So, now we are starting the second segment in module 3. We will see a few definitions and introduce the next tail bound. So, the definitions will particularly be the kth moment, use that to in particular the second moment will be used to define something called the variance and a related notion called the covariance. We will run through some examples to understand the notion of variance and use the variance to get a better bound called the Chebyshev's inequality, and we will see that the binomial distribution is captured better by the Chebyshev's inequality. That is the goal for this segment. The kth moment is simply this, it is E, the expectation of x to the k. Okay. And the first moment is something that you have already seen extensively, that is nothing but the expectation. E of x to the 1 is just E of x, that is expectation. The second moment along with the first moment yields the notion of variance, and if you recall, if you look at the second moment, x to x squared, it is a convex function, right. So, E of x squared is going to be greater than E of x the whole squared, that was Jensen's inequality, right. And that difference, if you recall, when we looked at Jensen's inequality, we claimed that that difference actually measures how much the random variable deviates from the mean, and that is essentially the idea that we are going to capture here. So, variance of x is nothing but the expectation of x minus E of x squared. This is one definition. The other definition is E of x squared minus E of x the whole squared. Okay. So, E of x squared is nothing but the second moment, E of x is nothing but the first moment. Putting the two together, you get the variance. Okay. These two definitions are equivalent, and a quick homework for you would be to check that they are in fact equivalent. So, if you just apply the formulas and run through, you should be able to get them. So, let us now try to understand what is variance of x plus y, where x and y are two random variables. Remember, this is in line with how we approached expectation. We tried to understand what is expectation of the sum of two random variables, and we want to know if something similar comes up with variance as well. So, we apply the formula. Variance of x plus y is simply the expectation of remember we want x plus y. So, x plus y minus E of x plus y, which when you apply the linearity of expectation is going to be minus E of x minus E of y the whole squared. So, that is variance of x plus y, and I have colored it up in yellows and blues because I am going to regroup them in accordance to their colors. Its expectation of so here I am going to take the square, I am going to consider x minus E of x as one term and y minus E of y as the other term. So, and then when you square it, you are going to get all these terms, and then apply the linearity of expectation over all those terms. So, I will just skip that. So, essentially what you will get E of expectation of x minus E of x the whole squared plus expectation of y minus E of y the whole squared times some quantity. So, this expectation of x minus E of x the whole squared is nothing but variance of x, then you get variance of y plus 2 times this strange looking object here. Okay. And again, another small homework is if you work this out, it is actually going to be nothing but E of x y minus E of x times E of y. And this strange object is called the covariance. This is, if you look at this, variance of x plus y we have shown is variance of x plus variance of y plus something. Okay. We want to know whether that something becomes a 0, okay, and what is the condition under which it becomes 0, because that then relates to the expectation, because there E of x equal to E of x plus y would have been equal to E of x plus E of y. So, this object will become a 0 when these two terms are equal, right. So, can they be made equal? What condition will they be made equal? So, let us actually work that out. E of x times y, you apply the formula, it is summation over x, summation over y, x y times the probability that x equal to x and y equal to y. You apply all the formulas, but then you are stuck here. You do not know what to do with probability of x equal to x intersected with y equal to y, except when the two random variables are independent. If the two random variables are independent, then you can replace it with x equal to x times y equal to y, in which case it works out to be e of x times e of y. All right. So, essentially what that means is that when the two random variables x and y are independent, you will get the get something similar to linearity of expectation, otherwise you will lose the linearity of expectation. But nevertheless, we can this quantity, this covariance actually has some meaning, because if it is independent it is equal. What if it is not independent? There is some meaning to it. So, the best way to at least get some sense of it is to actually work out some examples. So, let us take two random variables, let us say they are outcomes of coin tosses, and 1 if it is heads, 0 if it is tails, or something like that. Okay. In this case, so what is this quantity of x y minus e of x times e of y? It should be immediate, it is 0. Why? Because these are two independent random variables. Okay. So, let us do something silly here. Let us limit the sample space to one of these. So, let us just focus on this one. Okay. So, this in this case we are not considering this outcome. So, the sample space is limited to the three outcomes shown in red. Okay. So, then now and let us say this is always x comma y. So, what is the expectation of x here? Expectation of x, there are this one is 0, 0 and 1. So, the expectation of x is 1/3, right. So, I am trying to work out this thing. Expectation of y, what is the expectation of y? Yeah, so that is also 1/3. Okay. And what is the expectation of x times y? 0. Why? Because at least one of them is always remaining as 0. So, it is going to be minus 1/9, and you can work out something like that for this other example shown here as well. Okay. Let us do something similar. What about this case? So, let us again pick the one that will. Okay. So, here let us again work on this one. Okay. So, what is the expectation of x here? It is going to be 2/3. What is the expectation of y? It is going to be 1/3. What is the expectation of x times y? 1/3. And so, that will turn out to be 1/3 minus 2/9, right. So, it is going to be plus 1/9. What do you think will be the case over here? Well, e of x y is in this case is e of x times y is 0 minus 1/4. Here, if you work it out, it is going to be, what is that going to be? What is e of x times y? It's going to be a half minus e of x again minus 1/4, I think, okay, equal to plus 1/4. Why are we going through all of this? So, it's what we sort of guess is it's ranging from minus 1/4 to plus 1/4. What is this measure telling you? So, why is this, for example, this 1/4? What is the intuition here as to why the covariance is maximized here? Yes, it is like you have tied the two coins together. So, if one happens to be at tails, the other one also is at tails. So, they are what is called positively correlated. Okay. Whereas, here you have tied them together, but you have tied them so that when one appears tails, the other one appears heads always. So, they are negatively correlated. When one is high, the other one automatically becomes slow and so on. Okay. So, this covariance actually is a very meaningful object. It actually measures how connected these two variables are. Okay. And when they are completely unconnected, or the technical term being independent, it is equal to a 0. Right. So, this is a very useful object, but for our purposes we will stop at this level of intuition, because what we want to do is use this the notion of variance to go on to tail bounds, but I wanted to make sure this notion is also clear in our minds, at least at the intuitive level. Okay. So, let us quickly look at some variances. So, let us look at the Bernoulli random variable. So, x equal to 1 with probability p, 0 with probability 1 minus p. The expectation of x is p, expectation of x squared is also p, because when you square 0 1 random variable, it remains a 0 1 random variable, right. So, the variance of x, you run it through the formula, you are going to get p times 1 minus p. The binomial random variable is just the summation of n Bernoulli random variables. So, you just, due to independence, you can just sum them up. So, you get n times p into 1 minus p. Geometric random variable, on the other hand, is a little bit more tricky, because you do not have this neat summation. You do not know how long you are going to do these iterations, right.
In the binomial case, they are independent. That's why.
Sorry, did I say dependent?
No.
Yeah, they are independent. That is why the variance of y can be written as the sum of the variance of the individual xi's. So, here I am using xi to denote.
How do you, like, can you get a similar expression for covariance here? Like,
yeah, the covariances will be 0, right. Oh, I see. You're talking about the more general thing where it's not just x plus y. Yeah, so there is. Yeah, that will be a little bit more complicated thing, but it's something that can be written. Okay. But since all of those covariance terms are going to be 0 because of independence. So, let us so we are kind of sweeping some details under the rug for now, but essentially since all the covariance terms are going to be 0, just you.
Let us now consider the geometric random variable. X is a geometric random variable and it has parameter p. So, this means you toss a coin with bias p until you see the first heads. And by now we should know that the expectation of x is 1 over p. You can work that out. Our question now is, what is the variance of this random variable x? And towards understanding the variance, we first want to compute E of x squared, and that's what we're going to do now. Let's consider what E of x squared is, and we'll write it out using the law of total expectation. Now, x squared, to compute x squared, you can we break the universe into two parts. The first part corresponds to where the first coin flip lands tails, and the second part corresponds to the first flip landing heads. Okay, so now our expectation of x squared is split into these two parts, and of course they have to be weighted by their corresponding probabilities. Okay, and let's look at this expression. Let's look at the second one, the one where the first flip is heads. If the first flip is heads, then x is going to be 1 because you've seen the heads and therefore you're not going to toss anymore. So then x squared is also going to be 1. So this whole term becomes a 1. Okay, and we know the probability of flipping a heads is p because it's a p biased coin. Okay, so that leads us to just the term p, because this is just going to be a 1. So the second term here is just going to be p. Let us now consider this first expression, well, the probability that the first flip is a tails is 1 minus p, and that we have. And let's consider what happens when the first flip is tails. After the first flip, you really have to, this is the geometric random variable, so there is this memorylessness property. So you have to set aside the first coin toss, and then now again start all over and wait for the first heads to occur. So in essence, after the first flip has been set aside, you really are in a situation where you have to repeat the geometric random variable from the start. So that's why we have x prime, which is another geometric random variable with the same parameter p, plus 1. This 1 is where you set aside the first coin toss, and then you start over with the geometric random variable x prime. So that's, and this whole thing is within a square, so it's going to be x prime plus 1 the whole square. Okay, and we want the expectation of that. That's going to be this part. Okay, and now we can, since it's a square, you can apply the formula and then apply linearity of expectation, and we will be getting e of x squared plus 2e of x prime, I mean e of x prime squared rather, plus 1. Okay. And so this, when we expand it out, we're going to get this expression for the expectation of x squared. Okay. But that's just the expectation of x squared. The variance is given by the expectation of x squared minus the expectation of x the whole squared. That's the formula for variance, if you recall. So if you apply that, you're going to end up with the variance of a geometric random variable with parameter p being 1 minus p over p squared. Okay. So with that, we've seen a couple of examples of the of computing the variance for random variables. We are now ready to talk about this tail inequality called the Chebyshev's inequality. And as you may expect, this Chebyshev's inequality depends on the variance of a random variable. So in order to be able to apply this inequality, you need to know the variance of that of the random variable. Okay, so let's take x to be any random variable. Now notice that x need not be non-negative. X can be anything. Okay, and now a is some parameter. In this context, we're not just going to bound the upper tail like we did in Markov's inequality. We're going to bound both the upper and the lower tails. Okay, so in precisely speaking, we are interested in x minus e of x, the absolute value, being larger than a. And if you think about that, it corresponds to these regions within the distribution. So this is your expectation, and you want to know, you want to talk about x minus the expectation of x. Okay, so that can fall anywhere on this line. And you are in particular interested in the event that this x minus e of x is greater than a. So it has to be greater than a, or because we consider the absolute value, x minus e of x has to be less than a. These are the two things that we care about, and that's why these areas under these shaded portions is what we care about. And that tail is given to be the variance of the random variable x divided by a squared. So this is Chebyshev's inequality. And it's not hard to prove this. So let's see how this can be proved. So this is what we want. Okay, it's just straight from here. And inside this probability, we have this event, x minus e of x absolute value is greater than or equal to a. Now, just square the terms on both sides of this inequality of this event. Okay. It's not going to change the event at all. In fact, it has this nice property that it gets rid of the absolute term. And this square on the left side is going to be non-negative. Okay. And so this x minus, now what we have is the probability, this term becomes the probability that x minus e of x the whole square is greater than or equal to a squared. And because this is a positive term, a non-negative term, we can simply apply Markov's inequality. And you can now see that this tail inequality, this more fancy looking tail inequality essentially depends on Markov's inequality. Okay? So this is a positive term and there's an a squared, a parameter here, a squared in this context. So then we can apply Markov's inequality and we get the expectation of this. This is, by the way, a random variable, right? So the expectation of that random variable divided by a squared. That's just Markov's inequality. And what is the expectation of x minus e of x the whole square? That's nothing but the variance of x. That's just another formula for the variance of x. And so it's going to be variance of x divided by a squared, which is exactly Chebyshev's inequality. Okay. And the same inequality can be slightly rewritten. So you can rewrite it in a couple of forms. So here's one form. So if you write this tail as t times the expectation of x, you simply get t in over here. It's going to be the square of whatever you put in over here. So it's going to be variance of x divided by t squared times e of x the whole square. Okay. And now another form, let's define a term called the standard deviation, often denoted sigma of x. This is nothing but the standard deviation. Okay. And that's nothing but the square root of the variance of the random variable. Okay. The nice thing about the standard deviation is it's in the same units as that of the random variable x. Suppose x measures, say, distance in meters. Variance is e of x squared minus e of x the whole squared. So when you think about it, the unit is going to be meters squared. Whereas the standard deviation is going to take a square root of the variance and therefore it's going to bring it back to meters. Okay. So that's one of the nice features about the standard deviation, and so it's quite commonly used in practice. And a common question people ask about random variables is, where they relate to how large the standard deviation is, because that tells you how much the random variable is likely to deviate from its expectation. So what's the probability that a random variable will deviate from its expectation by more than t times the standard deviation of x? That's going to be at most 1 over t squared. Again, simply by applying Chebyshev's inequality. Now here it will be, what will we have over here? This will become variance of x divided by t squared times sigma of x the whole squared. But that's essentially just variance is nothing but sigma of x the whole squared. And so those two will cancel out. You'll be left with 1 over t squared. That's how you get this formula, this inequality. Okay. So let's go back to the binomial distribution and test out this new tail bound that we have, this Chebyshev's inequality. Remember that in our experiment in the last segment, we drew several samples from the binomial distribution with parameters 10,000 and bias 0.5. Okay. in particular, I mean, so this means that the expectation is going to be 5,000, and you can work out that the variance is going to be 2,500, which means that the standard deviation is going to be 15, just 2,500 square root of that. Okay. So now you can ask, what is the probability that x is going to deviate from the expectation by more than 150? Okay, if you recall, there was almost never, I mean, the number that we drew from the binomial distribution almost never went uh, beyond 5,650. I'm so sorry, 5,150, or it almost never went below 4,815. So it was within the plus or minus 150 range, and that's what we are asking. And if you work it out, this is going to turn out to be 1 over t squared. So t here is 3, and that's going to be 1 over 9. And this is a much better, more accurate probability bound. Okay, and so Chebyshev's is clearly more powerful than Markov's in this context, but in a strange way, it's essentially Markov's applied in a more appropriate way, and that's exactly what Chebyshev's is. Okay, so with that, we come to the end of our segment on Chebyshev's inequality. What we did was we introduced some definitions and some terms that were crucial to understanding Chebyshev's inequality, and we stated and proved it, and we showed that at least in the context of binomial random variables, it's a better way to bound the random variable than Markov's inequality. Okay. And in the next segment, we're going to go back to the problem of finding, I mean, of selecting the kth element. In fact, we'll stay a little bit simple. We'll just be interested in finding the median of a given array of numbers. But this time, the good thing is we're going to ensure that the running time is O of n with high probability, not just on expectation, but with high probability. So that's going to be the focus of next segment. Thank you.